We call a collection of measurement statistics classical or non-contextual if it can be described by non-contextual hidden variables, of which local hidden variables is a special case. Today, we want to talk about contextuality when you fail to be able to describe something with non-contextual hidden variables, and we want to do this using triangles and pictures. Remember from last time that we added a third measurement, this XOR measurement, so that we can talk about measurement scenarios in terms of triangles. How does this work? I add an edge for Alice, an edge for Bob, and an edge for Charlie, where what Charlie does is add together the outcomes of Alice and Bob. This gives us more flexibility in gluing and putting together different interesting scenarios. And the way that and then the observations, the frequency of results that Alice, Bob, or Charlie see are obtained by computing the marginal distributions. You add up, for example, if I want to see the zero outcome for Alice, I add up these two. If I want to see the zero outcome for Bob, I add up these two. And the zero outcome for Charlie is given by adding up these two. And then the one outcome is comes from the complement. So it would be from these two for Alice, for example. Now let's talk about classical scenarios. What do we mean by calling something classical? What we mean in principle is that we can describe it as some sort of probabilistic mixture of sort of deterministic distributions. And remember, the deterministic distributions are consistent with the assumption of realism, that if we have two possible outcomes for Alice and Bob, A and B, that these correspond to like heads or tails or coins out there in the real world. So if we want to find out if something's classical or not, a distribution's classical or not, we need to figure out first what are the definite states that are possible in our measurement setup. So for a single deterministic triangle, we have that Alice can get an outcome 0 or 1, or Bob can have an outcome 0 or 1, and the outcome of Charlie is determined by the first two. So there's four possible choices because you have 2 to the 2. Alice or Bob could choose 0 or 1, so 0, 0, or sorry, not choose, but rather they get the outcome 0 or 1, so it could be 0, 0, 0, 1, 1, 0, or 1, 1. And Charlie's outcomes determined accordingly. So how do we figure out what this deterministic distribution looks like? The basic idea is that we want the when Alice gets 0 with 100% certainty, Bob gets 0 with 100% certainty, Charlie should also get 0 with 100% certainty. We want to impose the conditions that these marginal distributions are precisely 1. So P of X equals 1, with the 0 outcome is 1, 1, and 1. That means that these marginals here, this must be 1, this must be 1, and this must be 1. The only way to satisfy this is to put the 1 in the middle. Now, if I have this case where Alice gets 0, but Bob gets 1, then what does that mean? That means that the probability for Alice to get 0 should be 1. That the probability for Bob to get 0 should be 0, whereas the probability for Bob to get 1 should be 1, because that's what we're putting here. And then the probability for Charlie to get 1 will also be the sum of these two numbers, which is also 1. So we can do this for each of the 4 scenarios, and you get 4 deterministic distributions like this. Now, each triangle or each simplex is always classical. And the way that this works is as follows. I can put a distribution inside of this triangle. And the way that it works out for triangles and higher simplices, or also the lower simplex, the single dimensional line, is that the number of deterministic distributions is exactly the number of parameters that appears in the triangle. Not only that, the places where the 1s and 0s appear are precisely so as to fill out the entire distribution. You'll see what I mean in a second. So this distribution, I can write it as a probabilistic mixture of, say I take P00 and I multiply it by this distribution, by which I mean that I multiply it by each of the elements in it. So because these are all 0, those are 0, and all I get is the P00 goes in the middle. Now I can do the same thing for here. Same thing for this one and this one. And so I get that the most general distribution I can write down is always going to be expressible as a probabilistic mixture of these deterministic outcomes. So, like I said, the triangle is always classical or non-contextual. Now let's see a contextual scenario. So we talked about this as part of the exercise for the last thing, but I'll go over how this works. We have a cone. And by cone, what I mean is that I have a triangle and I glue two of the edges together. Say Alice and Bob's measurement get glued together. Let's not dwell on what this means physically, but mathematically we can do this. And it's enforced by the fact that the sum of these two numbers has to equal the sum of these two numbers. And we call it a cone precisely because when we glue the two together, this bottom part gets wrapped around into like a little circle, and you have this pointed tip, so it's topologically a cone. Now, the no signaling conditions mean that these two numbers equal these two. When I set up the equation, I see that my P00 drops out, and what that means is that these two parameters are equal. And so I'll just call them Q to reduce the clutter. So I can rewrite this general distribution with one less parameter. I'll call the P01 and P10 Q. And then for simplicity, I will call P00 as P, and I will call P11 as R. Now I also have to satisfy normalization. So I add up everything in here. That means that 2Q plus P plus R equals 1. And what that means is that I can solve for one of these parameters in terms of the others. Now I can choose any one to solve for, but it'll look a little bit more symmetric if I solve for Q instead of P or R. So I want to treat P and R as sort of like independent variables. And so Q can be expressed as 1 minus P minus R, all divided by 2. And of course, because we have these minus signs, it's going to be important to enforce the condition that this is greater than or equal to 0, because in principle, we could choose P equals to R equals to 1, and then this will be a negative number. We want to avoid that for it to be a proper distribution. Because remember, these probabilities are coming in. One way of looking at it is that they're coming from frequencies, coming from an actual performed experiment. You shouldn't have negative frequencies. So that's why you're enforcing this. So let's see how this is actually contextual, or that there are contextual distributions. There are also classical distributions, though. So the way that this works is we need to, again, enumerate all of the classical or deterministic distributions. So because I'm essentially identifying this edge and this edge together, then the outcomes should always be the same for the two. So Alice can get 0, or Alice can get 0. Alice can get 1, and Alice can get 1. And in both cases, the sum modulo 2 is 0. And using the same sort of strategy we had before, the probability for this edge to get outcome 0 should be 1. And then this one should also be 1. And then this one should also be 1. Therefore, you have to put the 1 in the middle. Now, for this one, we want the probability that Alice gets 1 to be 100%. So that means that this needs to be 1, and this needs to be 1 for this edge, so that these marginals are 0. And similarly, for Charlie, is still the probability of getting 0 is 1 still. So something is not classical or contextual if we can't write it as a probabilistic mixture of these two. So I propose to you that there's a distribution that looks like this, and that this distribution can't be written as a probabilistic mixture like this, even though it satisfies all the conditions above. Namely, we want this, the sum of these two numbers, to be equal to the sum of these two numbers. That's satisfied. And the whole thing is normalized because the sum is equal to 1. So this is a perfectly valid distribution on this cone scenario. However, it is not a classical distribution, because the only possible classical distributions we have is by multiplying a non-negative number by this distribution plus 1 minus that number because there's only two of them. So the only places that I get non-zero entries are here and here. But here I actually have non-zero entries on the other 2 points. So that actually means that we can't write it like this. Therefore, it is non-classical. To see what this looks like geometrically, anything that can be written classically should be, this is going to be part of the classical region or the Bell polytope. Let's see what the geometry of these distributions looks like. So what we want for any distribution is that we need these numbers to be non-negative and normalized. So using Q as described in here, we have that it's automatically normalized because I impose this automatically. So what I require is that P be greater than 0, R is greater than or equal to 0, and Q is greater than or equal to 0. So those are inequalities that I have to satisfy. So let me consider a two-dimensional space with the x-axis given by P, the y-axis given by R, and I have these inequalities. P greater than or equal to 0 gives me everything above this x-axis. R greater than or equal to 0 is everything to the right of this y-axis. And then what is this Q inequality telling me? Well, let's rearrange it. I can always multiply by 2 on both sides. 0 stays 0. Rearranging the 1 to the other side, or the P and R to the other side rather, I get P plus R is less than or equal to 1. Or I have that R is less than or equal to 1 minus P. So what's going on there is that I have a line 1 minus P, which goes down linearly like so, and R needs to be less than that. So that's another inequality. So we can see geometrically the vertices are at the intersections of these inequalities, just like this, and there's 3 of them. The deterministic ones are precisely these, R equals 1 and P equals 1. Let's see what that looks like up here. When R is equal to 1 and P is equal to 0, this is 0, obviously, but then you also have that Q is equal to 0. So you have that this is 1, 0, 0, 0. Alternatively, you have the case where P is equal to 1, this is equal to 0. You get again that Q is equal to 0. So then you get this deterministic distribution. So suffices to say that this and this are my 2 deterministic distributions. Everything that's classical is a probabilistic mixture of everything that's between these 2 vertices. So this is my Bell polytope in a sense. It's just a single line that's bounded at the 2 edges. But this is everything that's possibly classical, just like this. Now that means that everything that's not on this line, that's this entire region here, is non-classical. So we have this vertex here when Q is equal to 1/2, P and R are equal to 0. So that's precisely this distribution right here. That is in fact a vertex. It lies at this corner right here. And it's, if we want to write anything that's inside of this region, it needs to include actually this as a, as part of the probabilistic mixture. But the point is that you have something that's outside of this line, and this, by definition, anything that's outside of this line is non-classical. So here we have a geometric illustration of what the no signaling polytope looks like. Perhaps this is the simplest possible demonstration.